Now we go on to the Taylor series expansion of a complex function f of z about the point z equal to z naught. And it is given by the formula, which the first term is the original function, which is substituted by the given point z naught. The second term is z minus z naught multiplied by the first derivative of f of z substituted with that point z naught. The third term, z minus z naught all squared divided by 2 factorial multiplied by f double prime, which is the second derivative of f of z substituted with z naught, and so on. Note that the power of z minus z naught also determines the number of derivatives. So if you can recall that if the power of z minus z naught is 3, you divide by 3 factorial, and it means f is differentiated 3 times, and you substitute into your answer the given point z naught. But then again, if the value of z naught is equal to 0, then the Taylor series expansion is known as the Maclaurin series. Then in this example, f of z is given to be 1 over z into z minus 4j, and z is equal to 2j. In our partial fractions, note that we just decided to split that function into partial fractions just for ease of differentiation. So we got j over 4, and then for b, negative j over 4. And then remember, the first term of our Taylor series is f of z naught. So we substitute into our f 2j, and then we simplify. And then the second term requires us to have the first derivative of f of z. So we differentiated what we had there as partial fractions and easily did that, and then we substitute our 2j in to get the answer. Please check all these answers to see whether you're getting the same. And then the second derivative of f, it means all you need to do is just to differentiate f prime to get the second derivative. And then into it you substitute 2j. That gives us the third term. And then we continue doing so. Note that most of the time you will be told how far you are supposed to go in your differentiation. Sometimes the questions would be saying up to the third non-zero term. Sometimes they would say up to the term that has got z to the power 4. So you must know how far you need to go. So it's important that you read the instructions of that particular question. So here we've gone up to the third derivative, and we got the third derivative substituted by 2j to be equal to 0. And then f of z, we just wrote down the definition of the Taylor series, and then into it substitute. For f of z naught, 1 over 4. Note that z naught has been given to be 2j, and then f prime of z naught, we calculated it, and then again the term z minus z naught all squared, you substitute z naught for 2j, and then the second derivative of f substituted by z naught, you substitute it in, and then we simplify. Note that those terms z minus 2j, z minus 2j all squared must remain in your expansion. Number 2, we got f of z equal to 1 over z squared, and we've got z equal to 1 plus j as our z naught. Once again, into our f, we substitute z0 in and simplify. Note that for all our simplifications, we make sure that we do not have j in the denominator. Then f prime of z gives us negative 2 over z cubed, and then we substitute 1 plus j. And then the second derivative of f, we got 6 over z power 4, substitute 1 plus j in to get negative 3 over 2. We went up to the third derivative once again, and it gave us 3 minus 3j when we substituted our z0 in. And then wrote down the definition of our Taylor series expansion, and then substitute all the values in and then simplify. Please do check whether we got everything correctly. Here are some exercises. The first one, f of z is 3 over z into z minus 3 about z not equal to negative 1, and up to the first 3 non-zero terms. And we are supposed to do the Taylor series expansion, and then the Maclaurin series expansion up to the term z cubed. Then our f of z is that, and then we may factorize it and then find partial fractions. Remember, Maclaurin series means z0 is equal to 0 in our expansion. Then we go to singularities, zeros, and residues. We'll start with the definitions. A0 of a function or complex function f of z is always a point at which f of z is equal to 0. Then a singularity, also known as a pole, is a point where f of z is undefined. Note that if we've got a function which is a quotient, that means it's got a numerator and the denominator. In order for us to get the zeros, we equate the numerator to 0. In order for us to get the singularities of the poles, we equate the denominator to 0 and then solve. For this example, we given f of z equal to z minus 1 over z to the power 4 minus z squared into 1 plus j plus j. To find the zeros, we equate the numerator to 0 and then solve for z. And then for the singularities, we equate the denominator to 0 and factorize. Note that the factors of z to the power 4 is z squared and z squared. The factors of j is minus 1 times minus j. And then we know z squared minus 1 is a difference of 2 squares. In order for you to find the factors of z squared minus j, we use the Movers Theorem, which helps us to find the two roots, z equal to 1 plus j over the square root of 2, and z equal to minus 1 minus j over the square root of 2. Or it could just be 1 plus j into the square root of 2 over 2, minus 1 minus j into the square root of 2 over 2. And all of them are simple poles. The reason being, the power of those factors is 1. That's why we call them simple poles. That means the factors have power 1. Then the next one is sine of z minus 1, also divided by z to the power 4 minus z squared into 1 plus j. For the zeros, we've got sine of z minus 1 equal to 0. And we remember that 0 is equal to also sine n pi in general for n an integer. Therefore, sine of z minus 1 is equal to sine n pi, and then we equate the arguments of sine. That means we've got z minus 1 equal to n pi, and therefore z is equal to 1 plus n pi for n an integer. Singularities, we still have the same denominator that we had in the previous example. Number 3, f of z is equal to z plus j divided by z plus 2 all cubed into z minus 3. Note that for the zeros again, we equate the numerator to 0, getting z equal to negative j. And then for the singularities, we equate the denominator to 0. Then we have z is equal to negative 2. And note that we have to write pole of order 3 because of the power of that factor. And z is equal to 3 is a simple pole because the power here is 1. Then we go to residues. When you have a Laurent series expansion of a complex or an analytic function, then the first term of the principal part has got coefficient a negative 1. And that coefficient is what is known as the residue. So when you have a Laurent series expansion, the first term in the principal part gives you a coefficient which we call the residue. So I've given you an example here where f of z is equal to z over z minus 1 into 2 minus z, where modulus of z is between 1 and 2. Note that these are two circles, one with radius 1 and the other one is radius 2. Then partial fractions to try and find the Laurent series expansion, and then you split up that condition so that we have the modulus of z greater than 1, modulus of z less than 2, so that we know for the first term we take out z in the denominator because of the greater than expansion, and then for less than we take out the constant, and then this is what we got as our Laurent series expansion. Therefore, the first term in the principal part gives us a coefficient a to power negative 1. Hence, I've indicated here the coefficient of 1 over z is 1, which is our residue. But now, without the Laurent series expansion, we can be able to find residues of complex functions. Note that if we have a simple pole or simple poles, the formula that is used is that one. Please note that we have the limit as z approaches that pole, and we multiply f of z by the factor that gave us that particular pole to eliminate z minus z naught from the denominator of f of z before substituting z naught. But if the pole is of order m, then the formula, the second formula that to use requires that we also accommodate the order. In this manner, we have 1 over m minus 1 factorial, and we take the limit with the derivative now of m minus 1. Note that we have m here it means if it was order 3, that means in the denominator here you'll have 2 factorial, and the derivative will be the second derivative. So if it's order 3, second derivative, if it's order 2, first derivative. Note that you take the limit of the derivative of that term that gave you that pole multiplied by the original function. Let's do an example that will accommodate both these definitions. We have f of z equal to z squared minus 2z, all divided by z plus 1 all squared into z squared plus 4. Note that we have to find the poles when we want the residues, because we're substituting the poles into the formula. So we have z plus 1 all squared into z squared plus 4 equal to 0. And then we solve. So now we note that z equal to -1 is a double pole. So m is equal to 2. And then when you factorize z squared plus 4, it gives you z equal to 2j and z equal to -2j. The other two are simple poles, but the first one is a double pole. So it means we have to use the second definition of residues. So with m equal to 2, then we do the substitution. M equal to 2 in there. Even in the derivative, we've got m equal to 2, noting that even inside we have to have the term that gave us the pole z, which is z plus 1 all squared, times the original function. So that means z plus 1 all squared and z plus 1 all squared will cancel out. You will be left with the derivative of z squared minus 2z divided by z squared plus 4. And then find this derivative. This is a quotient, so we use the quotient rule. For a quotient rule, we always take the denominator up first and then differentiate the numerator, which gave us 2z minus 2 minus the numerator times the derivative of the denominator, and then divided by the denominator squared. Then substitute immediately the value of z naught, which is that -1. And then note also, once you substitute -1 in, you cannot write limit in there. We just give the answer. Now the next part is to find the residues for the simple poles. Recall that now for simple poles we don't have the derivative. It's just the limit as z approaches 2j of the term that gave you, or the factor that gave you, that pole multiplied by the original function. So that means in this case z minus 2j and z minus 2j cancel out. So you are left with z plus 1 all squared into z plus 2j in the denominator, and then you substitute 2j in. Note that after simplifying, we get j in the denominator, so we multiply by the complex conjugate of the denominator and then simplify, giving us that answer. Again, for the second one, z equal to -2j, we do the same. Note that the term that gave us z equal to -2j is z plus 2j. So z plus 2j and z plus 2j will cancel out, giving us those terms z squared minus 2z divided by z plus 1 all squared into z minus 2j. And then we substitute the limit in, or our value for the limit, which is -2j, giving us that term, and then we multiply by its complex conjugate. and we simplify, giving us the answer. Here are some exercises. We determine all of the above zeros, singularities, and residues. Zeros, singularities, and residues. So that means for the zeros is the numerator equated to 0 and solve. Singularities is the denominator equated to 0 and solve. Residues, you take your poles and be the ones that you use, whether it's double poles or triple poles or simple poles, you use the appropriate formula to get the residues. It will be very interesting on what you get as the answer to that numerator. Also, we have here e to the power j pi z. E to the power j pi z. Please don't forget, when necessary, to use Euler's formula if it is necessary.